Hi, so I'm gonna start in a few minutes. Okay, सारे और लोग आ जाएं तब तक ask questions क्योंकि मैंने इतना लंबा नहीं बनाया तो it's gonna be dependent on you guys asking questions. इसलिए please use your mics and yeah, don't make it awkward like I am right now. Right, so since कुछ और करने को नहीं है, maybe let's, I don't know, one by one, tell how much experience we have with physics in general. Like school तक ही पढ़ा है या खुद पढ़ते हैं, or is that just me? Right, so can we do that, or are you none of you really in the mood to talk? Okay, I'm guessing the latter.
Most of us.
Sir, Aslam sir, I just came. Is this the
My
lecture
guy.
from the society?
Yes, it is. And yeah, you don't have to call me sir. I'm literally as old as you are. So yeah.
Then if you don't mind, I just got just quick question. I know the title is supposed to be purposely humorous to bring in people, but like time travel, is it just on multiversal or linear? What he means?
Linear. Absolutely linear, because multiverse just introduces so many more variables that it's really more complicated for people who are just introduced to the chapter to understand. But honestly, no, if you want to think about it, when I'm describing it to you, you'll notice that both multiverse and linear are compatible with what I'm teaching. Not teaching, I mean describing, because there are two ways you can time travel, and one's multiverse and one's linear. So we're gonna get to it in it's cool. So I'm honestly glad you're here, because I know you ask questions, and I really want some questions.
Thank you very much, sir. I'm happy that we'll be discussing the grandfather paradox instead of the square circle paradox.
Okay, cool. So, कितने लोग हैं? 20. Like, I should just start, right?
Yeah.
Hello, y'all.
Maybe wait a couple
Hi,
of minutes.
hello. Okay, sure. We're waiting a couple of minutes. The fan isn't making noise, is it?
No.
No? Okay.
Don't worry, it's gonna be fine.
Also, you can, if you have any questions, you can just unmute yourselves and ask them right there at the moment.
Or would it be better if we
Yeah,
could
because,
raise hands and Heather himself could identify them, because वो flow खराब हो जाता है.
No, honestly, इतना मैंने काम नहीं करना. Just you guys just ask, just unmute yourself, interrupt me and ask the question, because मुझे भी समझ आती है. आखिर में either you'll forget the question, or it will be out of context, और ना मुझे समझ आएगी ना तुम लोगों को समझ आएगी. So just ask it as soon as you get it, right? Because that's the best.
Yeah.
चलो.
Or you can send them over to me on the Zoom chat, and I'll.
Yeah, if you don't want to use your mic, just
Guys,
chat.
the chat is disabled.
I don't know how to not disable it.
Ma'am.
Option होगा कोई.
Wait, I'm co-hosting.
Yes, I'll do that.
Okay, you all should be able to chat now. आगे है ना option?
Yep, clear हो गया.
Perfect.
Oh, did I just see Sir Majid? No, no. We have 30 participants. We can probably start.
I think we should now. Kafi ho gayi.
Yeah, you should.
Okay, hello. So we're going to start today. We're talking about time travel, right? So it's fun, it's interesting. It covers a lot of basic science concepts that if someone wants to study science, they're gonna probably come across. So two main fields in science. There's astrophysics, which is very big things like planets and how they work, and then there's quantum mechanics, which is how teeny tiny particles work, right? So we're going to cover a little bit of everything. We're going to get introduced to a little bit of everything. Uh, so as soon as my presentation starts working, yeah. Right, so I was very lazy in making this, so I'm going to speak most of the time, and there's not going to be much to see here. Uh, but so let me just tell you what we're going to do. First off, I'm going to tell you what time travel is, obviously, because I mean, all of you already know, we've all seen movies, but so the formal definition might help. And then we're going to discuss how to travel forward in time. We're going to discuss how to travel backwards in time and what works, what doesn't work, and why doesn't it work. And then in the end, we're going to discuss some cool paradoxes that could form because of time travel. We're going to discuss those. All right, so let us get to it. We're going to start by discussing what time travel is. All right, so this is not taken from Wikipedia, but time travel is a concept in which you move between different points in time. So if any one of you has ever seen Interstellar, you know how they do this thing with the pen and the paper? It's basically that, right? For example, if this is time, boom, it's moving forwards and backwards in time relative to how other people perceive time. It's a bit complicated because it's very relativistic when you're looking at time travel, or most physics in general. There's no one object, right? What you see is different from what the thing is experiencing. That's called relativity, and that's basically what Einstein kind of, in a nutshell, was explaining in his theory, right? So how to travel forwards in time, right? So the only way we know how is speed, right? So there's this theory called special relativity. It was coined by Einstein. It says that it's basically a theory on the effect of space-time when something's moving really fast in a straight line, right? So space-time is this fourth dimension. It's basically, someone said space and time are just linked together, and there's no changing that. They're just forever going to be linked together. If you change one, the other is going to get changed. Imagine this net stretching across the universe, right? It's a mixture of space and time. Now, two things basically affect this net, right? When you have something very heavy, or when something's moving very fast.
Mass
right?
and speed.
Mass and speed, yeah. So, imagine the universe is basically a big trampoline, right? When you jump on the trampoline, you're going to be making a big dent, right? That is how mass and speed affect space-time, right? So, when people say gravity is an effect, not a force, this is why gravity is an effect, not a force, right? When something's very massive, it affects space-time, like you can see on the screen, and anything near it is just going to fall down that curve, right? Just like in a trampoline, if someone's standing in the middle, you throw a ball, it's going to go towards the center because of the mass. That's basically what Einstein said in his theory of general relativity, right? So now we've seen that space-time specifically एक चीज के ऊपर क्या affect होता है, but when scientists thought, how do I travel forwards in time? They thought, right, so what effect on time does mass have? What effect does speed on mass have? So, for example, let's imagine we're in a spaceship and it's going really fast, right? It's going to curve space-time. It's going to distort space-time so that time for you passes slowly, right? This is called time dilation. It means when something's going really fast, time is going to pass slowly for it than for something that's or at rest or is slower, right? And this is not something that you need to go very fast at. For example, satellites, if I get like an atomic clock and I put it on a satellite and I put it in orbit, the time is going to go slower for that clock than it is for me on Earth at rest. You know, relativity, I'm going to be at rest. So this is not something that's, you know, theoretical. This is something that actually happens. You can actually go forward in time by going fast. There is maths to it. Yeah.
I'm sorry, but I may be wrong, but I also just heard a bit about this, that as Einstein said, that technically aren't we constantly going through time, but just at different rates? Like when you're sitting down and me and my brother are currently walking, doesn't that just mean
Yes,
that you are moving at a greater or faster time dilation through time, and
right.
just me and my brother's speed is
No,
higher,
so
we're technically move through time slower? Like Einstein put it,
so
the faster you move space, the slower you move through time.
so basically, you're not constantly moving, which is why Einstein has coined inertial frames of reference, right? It's something has to be stationary when you're doing this at all times. You're right, you just did describe time dilation exactly like I described it. When I'm sitting down, I am moving through space. But when you're looking at me, I am stationary because you need it for the experiment. And you are moving faster relative to me, right? So that is basically what this is. And this might get a little bit complicated. This is a bit hard to digest. Like even right now, I have difficulty comprehending the fact that there is a fourth dimension and how it works and everything. But all when you need to know is that speed is a factor that can slow time down, right? So I'm sure all of you have heard of the twins paradox, right? You have twins, right? And I decide to send one on a space mission for like let's say 50 years, and he's going really fast. Let's say like 1/4 the speed of light, right? When he comes back, he is going to be younger than his twin on the Earth, right? He'll have experienced less time in that spaceship than his twin on the Earth, and that's where the paradox arises. Are they twins or are they not twins? Because they're not the same age now. So you know, it's not a theory; it's fact. It will work, and it does work. So there's really not much I can talk about going forward in time. There's no debunking it because, well, as I said 3 times. So now we're going to get to traveling backwards in time, which is the more interesting and silly concept. So scientists, you know, were like, okay, so we can go forwards in time, but that's not interesting. What's interesting is going backwards in time. I want to go back and be able to kill Hitler. So they thought, right, so if speed is the answer to going forwards in time, why not speed being the answer to going backwards in time? So they basically you have normal speeds for humans, you know, walking, running, Bugattis. Then you have very fast speeds, you know, 1/4 the speed of light, half the speed of light, 99.99% the speed of light. And the third category is the speed of light and faster. So they thought, right, the first two, they aren't really going to help us. So maybe the last one is what's going to allow us to travel backwards in time. And so that's where this theory started. They thought if we could go faster than the speed of light, we could technically go backwards in time. And that's when this huge mess erupted because of how you just cannot go faster than the speed of light or even get to the speed of light, which is why this will never work. Speed will never work because of some basic concepts, right? So you see how time is affected because of speed, right? It's space-time. So I can't just affect time and say space won't be affected. Both are affected. So that means because time is slowing down, simultaneously space is also decreasing. The faster I go, the smaller I become, the shorter my length becomes. This is called Lorentz contractions. Basically, to get to the speed of light, something that has mass and occupies space will need to not occupy space anymore. The length will have to be zero for it to reach the speed of light, much less surpass it. You'll have to have negative mass to surpass it. And the implications of that are just weird. So that's one reason why you just can't go faster than the speed of light, because you won't exist if you go faster than the speed of light. And what follows is the other reason. So if I have to speed something up, I'll have to give it energy, right? And the more energy I give it, the more massive it becomes, because we've all heard E equals mc squared, right? Energy and mass are basically the same. The more energy I have, the more massive an object is. So it creates this paradox where I give it energy, it becomes more massive, it needs more energy. So I just keep giving it energy and it becomes more massive, it speeds up to the point where when it's at the speed of light, I'm going to need an infinite amount of energy to keep it going, right? Because it's just going to be infinitely massive. The more energy I'm giving it, the more massive it's becoming, and it's just going to snowball. And so we've established that if I want to go backwards in time, I'm going to have zero length and also simultaneously have infinite mass and also an infinite energy supply just lying around somewhere, so I can, go faster. So that's why that won't work. Now we're at closed time-like curves. This is something that most scientists hate because it's a mess. But it was proposed as an alternative to time travel, right? And this is where we get kind of into quantum mechanics. When you have closed time-like curves, what you basically have is a wormhole, but through time. So you know how I gave the wormhole meme? We're basically just going back to that. You're taking time, you're bending it, and you're ripping a hole through it so that you can cross back. How you do this? The theory behind it is that you take a black hole and you start just spinning it very fast, right? And so the space-time that's being distorted around it is just going to bend in such a way that it's going to go backwards in time. So a few problems arise when you look at closed time-like curves. First off, you see a black hole in the first place is what's hard, right? You need massive amounts of energy to maintain a black hole because of Hawking radiation, right? A black hole is constantly losing energy, and you just have to keep it maintained for it to keep it open, right? Now, what is Hawking radiation? This is a huge rabbit hole that we're going to fall down into. But Hawking radiation is basically particles that just pop into existence, right? So, like, if I take my fist, right, and I create a vacuum inside, and I mean a true vacuum, there's going to be nothing inside. Basically, what happens is if you take a microscope and you look, you're going to see particles pop into existence, right? You're going to see, electrons and positrons, right? They're going to pop into existence. They're going to react together. They're going to annihilate, and they're going to, they're going to disappear. This is what's happening everywhere around us, all the time, right? Particles are popping into existence, annihilating, and disappearing. So when you're near a black hole, what happens? Two particles pop into existence. The black hole has such a strong gravity, it attracts one into it. And so you just have this one particle that isn't going to disappear. So it leaves the sphere of influence of the black hole. It becomes Hawking radiation. So this loss of energy that the black hole is experiencing constantly, you are going to need to balance that. And you need tremendous amount. You need yottagrams of energy, which is a prefix I don't know if it exists or not. But it's basically, I think, 1/5 the energy the sun gives to the Earth in a year. It's a lot of energy. So opening a black hole it's really not feasible for that amount of time and for a large enough size for humans to pass through. So we can't really go into that. So scientists thought, okay, right, maybe we can do that. What else could we do? So that's where they got to, what if we don't transfer human beings as they are what if we transfer information? Because that way we don't need that much energy. We don't need a big black hole. We just need it open for a few milliseconds maybe, so we can transfer information backwards in time. And that's where you get into quantum mechanics, right? So basically, the idea is that you take your present self, you rearrange all your particles so it's exactly like that of your past self. And since both are the same, you're just going to automatically get transported to your past self. That's the idea. So for this, you need both to be linked, right? I'm going to need a channel through which I can transfer the information of my past self to my present self. So I can change this particle. So this is where quantum mechanics comes in, right? Some key terms we need to know first. Quantum mechanics has something called quantum states, and these are how I would describe a particle. So when you have a particle, you can describe its speed, you can describe its position, you can describe its spin, and everything together describes its quantum state, right? So they were like, I don't want to say speed every time I want to talk about this. I'm just going to call it its quantum state so it's easier. So what we want to do is I want to take every particle of mine and make it so that its quantum state is exactly the same as the one uh, that I want to go back in time to, right? So for that, what you need is quantum entanglement, and that is just this really interesting topic. This really interesting, not theory, it's really interesting thing that basically states that you can link two particles together in such a way that they both become the same, right? Or if I read information about one particle, I immediately know what the other particle is, even if they're light years apart. It doesn't matter how far apart they are. If I have, let's say, if I have this phone and I have another one, I don't know, halfway across the globe, right? If both of them are entangled, if I open this phone, instantly this other phone is supposed to open. That's what entanglement is, except with like really small particles. So they thought, okay, let's open a black hole, let's entangle myself with my past self, and then let's transmit information until both of them are the same. So that's when, right? So yeah, it's called a Bell state, right? When you link through time, it's called a Bell state. Um, so let's say I do this. Let's say I take my all the information that I would put to define myself. I throw it back in time, and my past self rearranges its molecules, or my past self gives me its information, and I rearrange my molecules so that I'm exactly the same. Right. So a quantum state describes what? Position, speed, spin, everything. So position, let's say. Right. So let's say I was in America when I want to go back in time. My particles were in America. My quantum state will change so that my particles go to America, right? Time is the same, right? My particles will change so they go back in time to when I was in America. And basically that's how it works. And this might be a bit hard to digest. So at this point, if any of you have any questions, I'm open to questions. Or
No
not.
questions.
Cool. Right. So I don't know if that's good or bad. You either have no idea what I'm saying or you're understanding it perfectly, and both of those scare me very much. So right. This is basically how I would travel back in time. So that you mentioned multiverse theory and linear time travel. Multiverse theory is something they came up with to kind of solve time travel issues, in which they said, we're going to make it so that every time you make a decision, you split into two separate universes, right? So if I say
Sir,
I want
isn't
to
that
drink water
sort of a
right
topic?
now,
Isn't another way to describe it Schrodinger's cat, or what's it called, Booker-DeWitt's branching theory?
I'm not sure. I can't hear you. What you say? Booker what?
Schrodinger
Okay.
cats or DeWitt's branching
Yes,
theory.
basically, it's Schrodinger's cat is what caused for this. So let me just give you a bit of background to what we're talking about. Some time ago, this guy got Schrodinger was sitting in a trench in World War II, and he just had this idea, right? He was a genius. He just thought, okay, so what
A
if I
box
put a
and
cat in a box, right, and I put this vial of poison in, right? That could break. That's very volatile. It could break at any second. And I closed the box, right? He said, right. So I'm not looking at the cat. I don't actually know if the cat is alive or if the cat is dead. So which is it? Is the vial broken or is the vial fixed? So this led to this huge half a century long debate that led to basically quantum mechanics being born. So he eventually said, okay, I've decided. I'm going to say the cat is both dead and alive, right? Deal with it. So if any one of you has ever taken AS physics, you've done superposition in waves, right? That's when two waves are completely aligned with each other. They're on top of each other. This is basic. I don't. This is basically it in a nutshell. Um, so you can be multiple things at once as long as you're not observing it, right? So this is just so mind bending. Some people were just like, "Nahi, no, is tarah kuch nahi karna." So that way they thought, right? So we're not going to say it's both dead and alive. We're going to say it's dead and alive in separate universes. So that in each universe it is only one thing. I don't want it to be two things in one universe. It's way too complicated. So that's where multiverse theory arose, right? They said every choice you make both choices at once, right? So if I say I want to drink I want to drink a glass of water, I'm going to go get up and go now. At this point in time, there's a universe in which I did get up, but in this universe, I'm not getting up. So that is how you have two multiverses or two parallel universes, and just try to imagine exactly how big this is. Every single decision you make is leading to two universes, right? Every single human being, every animal, every decision they make. So you really
So
just have
technically, every single decision you make branches off in infinite universes, and every one of those branches
right.
becomes
No,
even more infinite
right.
one,
No.
and
So
then those branches
you see
more and
how
more.
you can't have an infinite amount of superstates. You can only have a limited amount of superstates. So the cat can't be an infinite amount of things. It's either dead or it's alive. So it's only splitting into a numbered amount of universes. But when you combine everything together, the entire human race, every choice you make all the time, it goes to infinite because, yeah, so it's not every choice you make is leading to infinite universes. It's every choice you make is leading to a fixed number of universes, depending on the amount of choices you had. So that's where multiverse theory arose, and I have forgotten where I was. Right. So we were talking about right. So people thought, okay, so what if we apply this to time travel? What if I go back in time and kill my grandfather? I don't actually create a paradox. But if in one universe I don't exist anymore, and in one universe I do exist, and we're going to talk about the grandfather paradox in literally the next slide. But now we're going to talk about why closed time like ours will never work. So you know how I said you need a huge amount of energy to create a black hole big enough for people to pass through? Basically, there's also another complication. You're going to need an infinite amount, an infinite length for your black hole. It's going to need to be infinitely large so that you can create something that's plausible enough to go back in time. So, that's completely off the table. Now we say, right, but the other thing works, right? I can take my stuff, I can throw it back and throw information back, change everything, and go back in time. And that is where something called the no cloning theorem comes in, right? It says you can't have two things that are exactly the same. Why? Because of another thing in physics called the Heisenberg uncertainty. No, it's called the uncertainty principle, right? It basically means you can't know all the information about one thing, right? And when people say, like, I have two particles, I observe one thing from one and the other thing from the other, and I have a complete picture of the entire particle system, right? that is where you can't have that. The uncertainty principle is that if I have a particle, it's moving at a specific speed, right? I can't know its position and its speed at the same time, right? So people thought, okay, what if I measure this particle's position, I entangle it with something else, and I measure that particle's speed? I will have a complete picture of this. That's not supposed to be possible. That's why you have the no cloning theorem. It means you cannot completely make an exact copy of a particle. So if I transmit my past information to my future and I change my future self, I am completely wrecking the quantum states of my past self. Best case scenario, I get some weird sort of cancer. Worst case scenario, my particles forget how they work with each other and I just explode. So that's why traveling back in time is not possible, whichever way you do it. And so this leads me to the final slide, which is paradoxes. Paradoxes are statements that logically or physically, let's say, contradict themselves, right? So first we have the grandfather paradox. It says, what if I make a time machine, I go back in time, and I kill my grandfather before he gives birth to me, right? So if I'm never born, how do I make a time machine and go back in time? And if I don't go back in time, how do I kill my grandfather? And if I don't kill my grandfather, then I do make a time machine and I go back in time and do kill my grandfather. But if I do kill him, and this just leads to you can just go on forever, right? So this is the grandfather paradox. Then you have the information paradox, which is basically a paradox on how information starts and how it ends, right? So let's say, I taught some of you and y'all actually got general relativity, right? You say, okay, I'm going to go back in time. I'm going to teach Einstein this theory, right? And he learns from you. He takes all the credit. He publishes his theory, and you grow up. I learn from Einstein. You learn from me. So it creates this cycle, right? It's just this cycle of where did the information come from? Was it Einstein? Was it you? You learn from Einstein. Einstein learned from you. And does information have an start? Does information have an end? It's weird. So that's the information paradox. And then we have the causality paradox. This is one of my favorites. So like imagine I just get all high and mighty one day and I say I want to kill Hitler, right? So I go back in time, obviously, and I kill Hitler. What happens then? Hitler is dead. He doesn't grow up to do the things that he did. So I'll have no reason to actually go back and kill Hitler. So I won't. But then that means Hitler will live, which means he will do the things he did, which means I will go back in time and kill him. So that's another headache for you guys. That's pretty much all I have for today. I don't know how much time passed. Oh yeah, we're almost done. Right. So, woohoo! I am open to questions. And if none of y'all have any questions, I will go and die in bed. No? Nothing? Really?
Heather, I think you should
Ooh.
check the chat if there are any questions there.
All right. I completely thought we were supposed to read them. Come on. Oh my God, that's a lot of questions.
There are
Okay,
no
right.
questions
So,
in the chat. In my
right, there
chat.
are no questions in this tab. Okay. Yes, thank you, Vinod. Right, so there's nothing there. We're done, right? We're done?
Yes.
Cool.
Yes. You guys can unmute yourselves now and give him like a round of applause or something.
We're done. So, yes. Woohoo.
Good job, bro. That was fun.
Yes, so thank you everyone for attending. I think Heather's
Did we
internet
just
connection is.
disconnect? Wow.
Yeah, I think.
Okay, guys, thank you for coming. And we're going to be hosting more lectures like this in the near future
Yes.
on different topics. In
Also,
fact, you
if
guys can
anyone,
recommend some topics too, because we're open to
exactly.
everything.
If anyone wants to give a lecture, they can contact me and